So hi everyone, today you're welcome again to our class, tutorial class, online class on physics. Today we're looking at basic electricity 3, which is specifically meant for SS3 students in SS3, and also some sharp students in SS2. You're on Best Science Brain tutorial YouTube. If you are not subscribed to the channel or you came across the channel as a result of search on YouTube, you subscribe. How do you subscribe? You locate the channel's name, Best Science Brain. Then under the channel's name, you see a subscription icon that looks like a tiny bell. Tap on the bell only once and get subscribed. You have a regularly anytime. So today we are going to look at many questions, miscellaneous questions, many questions based on electricity. We have done the first video, we have done basic electricity 1, we have done basic electricity 2. If you have not watched those videos where I did the introduction, you can go and watch 1 and 2 before coming to 3. So we're going to solve a lot of problems on this video, and these questions will be drawn from past examination bodies like WAEC examination, Cambridge examination, GCE, also organized by WAEC and NECO, and then JAM examination. So we're looking at the question on the whiteboard that says a battery of 3 cells in series, each of EMF 2 volts and internal resistance 0.5 ohm is connected to a 2 ohm resistor in series with a parallel combination of 2 3 ohm resistors. Draw the circuit diagram. So let's get it again. We have a battery of 3 cells. So to draw the diagram, we draw a parallel line presents a cell. So since there are 3 cells and they are connected in series, so we have to draw 3 parallel lines, putting positive and negative terminal, positive, negative, positive and negative terminal for the 3 cells that are all in series. And each of them has EMF of 2 volts. 2 volts here, 2 volts there, and 2 volts. Internal resistance of 0.5 ohm. Internal resistance, as I say, resistance offered by the chemicals within terminals or within the poles of the cell. 0.5 ohm. Then is connected to a 2 ohm resistor in series. So we have to go down. So this is a 2 ohm resistor that is in series with the battery, with a parallel combination of 3 ohm resistor. So this 2 ohm resistor is connected with a parallel combination of 2 3 ohm resistor. Okay, so we now have 2 3 ohm resistor in parallel. 2 of them in parallel to the 2 ohm resistor, which is in series with the battery. So I have 3 ohm here, I have 3 ohm here. Then we are trying to establish or draw the circuit diagram. So that's what I'm doing here. Then you can now complete the diagram. So you can as well put an ammeter here to show reading of the current. Current comes out for negative pole of the battery, moves down, and then continues its journey. So this is the diagram for the question. You can see battery of 3 cells in series, 1, 2, 3. Each of EMF 2 volts, 2 volts, 2 volts, 2 volts. And internal resistance 0.5 each of them. It is connected to a 2 ohm resistor. This 2 ohm is an external resistor. 2 ohm resistor in series with the battery and with a parallel combination of 2 3 ohm in parallel. So that's the diagram we have here. Number A says calculate the effective external resistance. So what are the effective resistance? This one that are under that you do with rectangular boxes. They are called external resistance or resistors. So to solve this, we see that these two are in parallel. And as I say, when you have two resistors in parallel, you can use a shortcut, a short formula that says Rp equal to R1 times R2 all over R1 times R2. I know that somebody else can still use 1 over R equal to 1 over R1 plus 1 over R2. Any of them works, but this is faster method. So Rp, which is the total for the parallel, becomes, there are 3 times 3 all over 3 plus 3. And that will give us 9 over 6. And that will give us 1.5 ohms. So that is this. When we merge these two together, we now have only one resistor replacing these two as 1.5 ohm. Then connected now to the 2 ohm resistor. That is 2 ohm here now. So total resistor becomes 1.5 plus 2. That gives us 3.5 ohms. So the total external resistance is 3.5 ohms. That is the answer to question A, the effective external resistance. Okay, we'll go to question B. Question B says we should find the current in the circuit. Current flowing out from the battery is the current in the circuit. To find current in the circuit, you use the formula EI equal to E all over R plus R. E stands for the EMF of the cells. So since the cells are in series, the total EMF will now become E1 plus E2 plus E3. Adding the 3 EMF together. That's going to be 2 plus 2 plus 2. The EMF becomes 6 volts, the net EMF. Then we're getting our R today, which is this R stands for the total external resistance, which you saw from question A as 3.5 ohms. That's the total external resistance, that is 3.5 ohms. Then the small r here stands for the total internal resistance. The small r, the internal resistance, since the batteries are in series, their internal resistance will also be in series. That becomes 0.5 plus 0.5 plus another 0.5. That gives us 1.5 ohm. Applying this formula, current becomes EMF, which is 6 all over our R 3. That is this R, total external 3.5 plus total internal 1.5. That gives us 6 over 5. When we divide, our current becomes 1.2 amperes. So the current flowing in the circuit is 1.2 amperes. So you can see I'm working on the board. So see I'm working on the board, very clear and very precise. The next question says we should find the loss volts in battery. The loss volts in battery. Okay? To find the loss volt in battery, if I watch our first video, the loss volt in battery I say again by current times internal resistance. Current flowing the circuit obtained from question B is 1.2 amperes. This R stands for the total internal resistance, which is 0.5 added 3 times. That is 0.5 plus 0.5 plus 0.5. That gives us 1.5 ohms. The lost volt, which is current, 1.2 times 1.5. Now give us the lost volt in battery. So 1.2 times 1.5 will give us give us 1.8. The lost volt in battery is 1.8 volts as our answer. So the next question, which is question number D, that's where I error here, this should be D now. We're looking for the current in one of the 3 ohm resistors. So as you can see, this is a Y equation or a previous Y equation. So we're looking for the current in one of the 3 ohm resistors. So I will draw out this. I'm going to draw out the 3 ohm resistors. You see they are in parallel. Three ohm resistors. We know that the current passing through the 2 ohm resistor is the one coming from the battery, because the 2 ohm resistor and the battery are in series. And as I said in the previous video, when instruments are in series, they carry the amount of current. So the current coming out from the battery is the 1.2 amperes we calculate in equation B. So it's 1.2 amperes that will come out from the battery, and that will also pass through the 2 ohm resistor. So on reaching this point, the 1.2 amperes will split into 2, into I1 and I2. So when devices are connected in parallel, they will carry different amount of current. So this 1.2 amperes split into 2 at this junction into I1 and I2. So we can now say that I equal to I1 plus I2. Some of these will give us 1.2. So, and then when instruments are in parallel, we know that they will have the same potential difference, the same voltage. And from Ohm's law, current is voltage over resistance. So let's find the common potential difference. We now have I equal to, and your I is 1.2 equal to V all over R1 plus V over R2. So solving this out, we now have 1.2 equal to V all over, our R1 here stands for 3, and R2 also stands for 3 also. So we'll take the LCM as 3. 3 here is 1 times 1, V is V. 3 here is 1 times V is V, equal to 1.2. Cross multiply, have 3.6 equal to 2 volts. So the voltage becomes 3.6 over 2, which is 1.8. So the voltage across each of them is 1.8 volts. So since current is V over R, so I can use V over R1, or I can still use V over R2, since both R1 and R2 are equal to each other, etc. So now divide 1.8 we got here by 3. That gives us 0.60 amperes. To prove that you are correct, if I1 is 0.6, I2 is also 0.6, 0.6 plus 0.6 gives us 1.2, which is the current entering the circuit. You can check out our working and see that everything is fine. Okay, now we have a question on the board under SSC equation that says, or senior school, high school equation, that is WAEC or GCE question. That says a voltmeter is connected in parallel with a variable resistance R, capital R, which is in series with an ammeter and a cell. The cell is of EMF E and internal resistance small r. For one value R1 of the variable resistance, the ammeter reads 0.3 amperes and the voltmeter reads 0.9 volts. For another value R2 of the variable resistance, the ammeter reads 0.25 amperes and the voltmeter reads 1.0 volts. Neglecting the resistances of the meters, find R1, R2, E, and small letter r, SSE. So let's look at this problem, and then we have to first of all sketch the circuit. A voltmeter is connected in parallel with a variable resistance. So let this be the variable resistor, like the row starts with a symbol. Then the voltmeter is connected in parallel with it. So our voltmeter connected in parallel. Voltmeter is used to measure potential difference in parallel with the variable resistor. And then the resistor is in series with an ammeter. To move up, we can draw our ammeter here with an ammeter and a cell. The cell indicates a battery. So you can draw the cell up there. So you can see from this diagram, the cell, the ammeter, and the variable resistors are all in series, while the voltmeter is in parallel with the resistor. Current is coming out and then going forth. Okay, they say the cell is of EMF E. So we can place E here as the EMF of the cell, and internal resistance of the cell is small letter r. Then I say for one value R1, that means if the resistor reads R1, or the resistor, the ammeter now reads 0.3 amperes. Then, and the voltmeter reads 0.9 volts. So when current is 0.3 amperes, the variable resistor records R1 and voltmeter records 0.9 volts. And now I say for another value R2, that means we're going to have two diagrams. I have another diagram again. The EMF on the battery remains constant, doesn't change. Likewise, the internal resistance. So E here, R. So when the current is giving us, okay, when the resistor value of resistor is R2, from the equation, the voltmeter reads for another value of R2, for another value R2 of variable resistor, the ammeter reads 0.25. So the current here is now, so when the resistance is changed to R2, current now becomes 0.25. And then the voltmeter reads 1.0 volts. So that's the diagram we'll have. We'll have two diagrams, we'll have two different types of, two different sets of conditions. And we are now asked to find, the EMF, the internal resistance, and then the value of R1 and then R2. Let's take a look at the question again. So a voltmeter is connected in parallel with a variable resistance R, big R, which is in series with an ammeter and a cell. the cell is of EMF capital E and internal resistance small r. For one value R1 of the variable resistance, diameter is 0.3 amperes and the voltmeter is 0.9 volts, which is what we have in this diagram, Venn diagram. For another value R2, which is this, or the variable resistance, diameter is 0.25 amperes and the voltmeter is 1.0 volts. Neglecting resistances of the meters, find R1, R2, E, and small letter r. Okay, let us now go to the solution. Before we solve, let's call this diagram Fig 1. Let's call this diagram Fig 2. Then from Fig 1, our current is 0.3 amperes following the circuit. Our resistance is R1. Let's get R1 first, and then our potential difference across the resistor is 0.9 volts. So we can get our resistance because we can apply Ohm's law. Ohm's law says current is voltage over resistance. We can make R the subject. R becomes voltage over current. The voltage here across the resistor is 0.9 volts. The current is 0.3. If you divide, the resistance R1 is equivalent to 3 ohms for the Fig 1. Then for Fig 2, to solve Fig 2, the same current flowing in the external battery, in the external circuit is 0.25 amperes. And mind you, this current coming out from the battery is also the same current flowing through the resistor because the resistor is in series with the battery. So the resistance is R2, then the potential difference of voltage across the resistor is 1.0 volts. Applying the same Ohm's law, our R becomes voltage over current, which is 1 over 0.25, which gives us 4 ohms. So our R2 is 4 ohms. So applying Ohm's law, we can find our R1 and our R2. So look at our working as we go to find E and small r. Okay, for us to find E, we want to wipe this side and continue. We already established that our R1 is 3 ohms and that our R2 is 4 ohms. To find the electromotive force and the internal resistance, we apply the circuit equation, which says current is given as E all over the external resistance plus internal resistance. We make E the subject. E becomes I bracket R plus small r. We open the bracket to have E equal to IR plus I small r. But we know that IR is nothing but the potential difference, which are given to us in the diagram as 0.9 for the first one and 1.0 for the second one. So we substitute IR with V. We now have E equal to V plus I small r, because V represents now current times external resistance. We now make our substitution from Fig 1. E is EMF unknown. So from Fig 1, the VD across the resistor is 0.9 volts. Replace V with 0.9, and then the current flowing through Fig 1 is through the resistor in Fig 1 is 0.3. Replace I with 0.3, and then we're looking for small r. That small r stands for the internal resistance. So we don't know E, we don't know R. This is from Fig 1. Then from Fig 2, do the same thing. E equal to the potential difference in fig 2 is 1 volts. Now I say 1 here in place of V plus the current flowing through the resistor is 0.25. Now I say plus 0.25 R, equation 2. So having obtained these two equations, we form a pair of simultaneous equations. This is E, this is also E. That means equation 1 and equation 2 are equal to each other. So we can now say we equate them 0.9 plus 0.3 R equal to 1 plus 0.25 R. We'll collect like terms. We now have 0.9 minus 1, or the other way around, you can just say 0.3 R minus 0.25 R equal to 1 minus 0.9. When I subtract this, I'm going to have 0.05 R equal to 0.1. We make R the subject of the formula. R now becomes 1 all over 0.05. So the value of our small r becomes 2 or 2 ohms. So the internal resistance of the battery is 2 ohm. Then we also find the EMF. To find the EMF of the cell used in the two cases, we take any of these equations, either equation 1 or equation 2, substitute the value of R into any of them and make E the subject. We find E. So let's use equation 1. E is equal to 0.9 plus 0.3 R. To replace R with 2, E becomes 0.9 plus 0.3 times 2. So that gives us 0.9 plus 0.6, which gives us 1.5 volts as the electromotive force. Third question, a cell of EMF E and internal resistance R, small r, was connected in series with two external resistors A and B of 4 ohm and 2.5 ohm respectively. When a high resistance voltmeter was connected across A, the reading was found to be 2 volts. When another resistor of 4 ohms, was connected parallel to A, and the voltmeter across A and B, the voltmeter reads 3 volts. Question A. Draw the circuit diagrams of the two arrangements. B. Calculate the EMF and internal resistance of the cell. So we're going to draw the diagram. We have to understand the question. From the first sentence, a cell of EMF E. So let me present the cell. Parallel lines, one positive, one negative, one longer than the negative one, E. Then the resistance R was connected in series to two external resistors, A and B. The resistors are placed on the other side. Two external resistors, A and B. You can call this one A, call this one B. Of 4 ohms and 2.5 ohms respectively. So A is 4 ohms, B is 2.5 ohms. And they say when a high resistance voltmeter was connected across A. So let's assume that a voltmeter across A. So when a voltmeter was connected across A, the reading was found to be 2 volts. So the voltmeter now reads 2 volts across A. Then when another resistor, that's go to draw another diagram now. Did the cell again, E, that resistance R. Then we have the resistors A and then B. So this is B, this is A. And we're told when another resistor of 4 ohms was connected in parallel to A. Remember that A already is 4 ohms, B is 2.5 ohms. So A is 4 ohms, B is 2.5 ohms. You see, another resistor is connected when another resistor of 4 ohms was connected parallel to A. So we have another resistor that is in parallel to A, and that resistor is 4 ohms as well. So when another resistor was connected parallel to A, and the voltmeter connected across A, B. Voltmeter now is connected across A and B. It reads 3 volts. So I have a diagram. So we have this. So there are the 2 diagrams required for the setup. And we ask us calculate the EMF and the internal resistance of the cell. Find the EMF and internal resistance of the cell. So we're going to call this diagram Fig 1. Call this one Fig 2. So let's go through the question again. A cell of EMF E, internal resistance R, was connected in series with 2 external resistors A and B. You can see the connection to A and B. And then A is 4 ohms, B is 2.5 ohms. When a high resistance voltmeter, that is voltmeter, was connected across A, only A, the reading is 2 volts. That is for this diagram. When another resistor of 4 ohms was connected in parallel to A, you can see A and that 4 ohms parallel to it, the voltmeter reads 3 volts. That is, okay, when another resistor of 4 ohms, you can see that, connected in parallel to A, and the voltmeter across A, B, it now reads 3 volts. We now have to draw the circuit, we have done that, and then find the EMF and internal resistance of the cell. So to solve this problem now, let's start with Fig 1. From Fig 1, let's find the current flowing through A. So for Fig 1, the resistance of A is 4 ohms. And then the potential difference across A is 2 volts. We know from Ohm's law, current is voltage over resistance. We're going to give us 2 over 4, that gives us 0.5 amperes. So this is the current that is passing through A. And this current passing through A will receive the same current that will pass through B. Why is this so? Because the 2 instruments are in series. So when they are in series, the same current will pass through them. And that also is the current that is coming out from the battery, because the 3 are in series with the battery. So the main current in the circuit is 0.5 ohms. Now, let us find the combined resistance. The total resistance in the circuit, Fig 1, is going to be 4 plus 2.5, you know, 6.5. Why is it 4 plus 2? Because the 2 are in series. Then let us now find the total PD across A and B. Mind you, we are given the PD across A only. So the PD across A and B Going by Ohm's law, making V the subject here. V is current times resistance. So the current is 0.5, resistance is 6.5. Having done that, our total PD across A and B, which we call DT, will now become 3.25 volts. Having done that, let's go to Fig 2. In Fig 2, we are given, we're given the total PD already. The total PD across the system of resistors is 3 volts, so we're not looking for it. And then we have to find the total resistance. Two resistors are in parallel here. That is the 4 ohm, 4 ohm. So total of the resistors in parallel, we use the formula product over sum, which is 4 times 4 over 4 plus 4. 4 times 4 is 16, 4 plus 4 is 8. We divide 16 by 8, we have 2 ohms. For the parallel connection. So total resistance now becomes 2 plus what we have is 2.5. That gives us 4.5 ohms. So having done that, we have gotten the information that we need. We now go to the circuit equation that says current equal to R plus small r equal to E all over R plus small r, big R plus small r. E becomes, maybe from applying IR plus I small r. Since we know our potential differences, this is 3.25 total here, this is 3 volts. We can say E is equal to V plus IR. Noting that our V is current times resistance. Now, if we come back to equation 1, for equation 1, our E becomes the total PD is 3.25 plus our current flowing in the circuit is 0.5, then multiply by R. Then for equation 2, we have to still make the same substitution for equation 2. But before we do that for equation 2, we need to find the current flowing in the circuit for equation 2, which we neglected. We have to use the current here. The current in equation 2, using Ohm's law, I equal to V over R. The value of our V is 3. The value of our R is 4.5. We divide 3 by 4.5. When we divide 3 by 4.5, we'll be getting 0.67. 0.67 amperes as our current flowing in this circuit. So we make a substitution our E for going to equation 2 using this formula. The value of our V is 3 plus, then current is 0.67, then multiply by R. This is for equation 1 and this is for equation 2. You can take a look at our working before we continue. Okay, having done that, from these expressions we created here for equation 1, this is E, equation 2, this is also E. We can now equate them together. We now have 3.25 plus 0.5R equal to this, making this equal to this. 3 plus 0.767R. We will collect like terms, 3.25 minus 3, crossing over, equal to this one crossing 0.67R minus 0.5R. That gives us 0.25 equal to 0.17R. R becomes 0.25 all over 0.17. That becomes about 1.47 ohms, approximately 1.5 ohms at the internal resistance of the cell. Alright, to get our E, or the internal resistance, we'll either pick this equation or this one and make a substitution. Replace R with 1.5. So, using equation 1, E is 3.25 plus 0.5 R. We now substitute R with 1.5. I have 0.5 multiplied by 1.5. E becomes 3.25 plus 0.75. If you add, our EMF becomes 4 volts or 4.0 volts for the battery. So you can check our work and then tell us what